Weird day with passing back exams. Easy to forget to do certain things. Okay, we're back on track. Let me see if I can rewind. So we just had our exam, and for every exam that we have, we'll always have the summary statistics here. The average on this exam was 83.7%. And Calculus 2 is a tough course. I would consider that to be a really great average. And more impressively, there was a two-way tie at 100% perfect scores. So congratulations to those folks. I can't say who they are out of protection of student data, but I think it's impressive in this class. It's hard to get everything perfect. That just implies you've worked really hard at this, and that's what it takes to get through this kind of content. But any questions at all folks have about the exam itself that you'd like to take another look at or discuss? Okay, maybe one last parting bit of information with the exam is front page is always a little confusing. The exam score that I provide you is a fraction, but when I go to upload it into the Moodle system, it becomes a percentage. And it's different from your course score. The course score is computed by taking all of the homework that was due up to Friday of last week and rolling it in with your exam one grade. So that just gives you your rough standing in the class as of now. As far as going down the line here on the weeks, for midterm week, there won't be any special project or anything like that. I'm just going to update your course score on a week-by-week basis. And on that week there, when I update it on Friday or Sunday, if I'm behind on grading, that updated grade will become your midterm grade for the class. Then we'll do this whole thing all over again for exam 2 and go off on a break. So that's our plan so far. Well, any other questions, folks, about the announcements or otherwise? Okay, well, we are here, as this indicates, we're looking into the area of a surface of revolution, and some related facts were the prior section, section 8.1, we looked into the arc length function. It's a function that goes integrate from a to b, the square root, 1 plus dy dx squared dx. We found that we could rewrite this whole thing as length equals the integral from a to b ds, where ds is exactly that, is a differential. And now we're moving over to areas, surface areas, but specific kinds where we take curves, not too different than these curves, where we're trying to find their lengths. We're going to rotate them either about the x-axis or the y-axis. And then imagine as some weird structure, maybe something that could be 3D printed. We want to know what's the surface area. If you had to paint it, how much paint are you going to have to use? That sort of thing is what we're going for. So in a certain sense, 8.1, 8.2, very similar topics, because there's not a whole lot difference that we're going to see in the formula here. But maybe before we jump into the new formulas, one thing I forgot to mention is if people were curious about this bizarre arc length application, this is a messy problem because it's real world data. It's kind of a tough one to attack because you have to get a degree 4 polynomial out. I found some challenges doing that in like Wolfram Alpha, for example. So my approach was, if you're curious on how to do this, I used a statistical software called R. That's its real name. You could freely download it here. With this syntax, it's a lot of stuff, but you could copy and paste it right in. All it did was it took the first coordinates in for x, second coordinates in for y, then it generated a degree 4 polynomial, and there's that polynomial. The plot is not a perfect fit, and we don't expect it to be. We're just modeling what we see in reality. So this is our best estimate of it. And it turns out that if you integrate all that stuff, you get the area of the property. I made computer technology do this part as well, because that's a tedious integration. From 0 to 400, because that's the extent of the property. Then anytime you do this kind of thing, work out mathematics using technology as heavily, you always need a sanity check. So applied problems, again, are messy. My sanity check was to imagine the property is a right triangle. That's the area of that right triangle. And it tells us probably we're on the right track. That's some decent numerical evidence that could be close to the right approximate area. But what we wanted was the length of that integral. Here's the formula that we put on the Moodle webpage. We have to take that polynomial curve, that one, the integrand here, differentiate it. Then after you differentiate it, square it, put in the root, take 1 minus, or that should have been a plus right there. Typo in my work. I think I got the right value, but that should have been a 1 plus altogether. So once we get this, that's my claim. That's the length of the stream, approximately 790.7 feet. Like before, we always need a sanity check. So what I did is measured the length of the hypotenuse through Pythagorean's theorem. And you know, they look like they're about on par. So that's one way to attack these kinds of problems. Sometimes our problems are even messier than this. Just imagine, instead of this, just a table of scientific data. If you have to do calculus on it, then statistics is going to enter the picture some way, shape, or form. So this would be one approach to make this all work. It's a very far out application, so it's not a question we could ask directly in the class. But I think it's a really honest kind of application of real world use of these kind of tools. So major reason to look at that is we're extending our function to this one. It almost looks the same. If you take this part out, that's the arc length. Throw this in, that's the area of the surface of revolution of the curve right here. So it's not a terrible function to write down, but sometimes it takes some work to just say, how does it all go together? And that kind of work is actually really important in section 8.2, because this formula we have here is only for rotation about x-axis. If we change this up and do a rotation about the y-axis, we get a different integral. This one has ds thrown in, so we're going to re-express it with what ds is. But the difference is that x right here, very highlight worthy. If you rotate about the y-axis, there's an x in the problem. If you rotate about the x-axis, there's a y in the problem. And spotting the difference is going to give us a lot of help on just setting these up in a homework setting, an exam setting, and so on. And maybe one over extra topic. We saw this happen once in section 8.1. It'll happen again on these notes here. We ordinarily think of curves being defined this way, y equals f of x. But occasionally your curve could be described this way. X is the dependent variable, y is the independent variable. We just make some small adjustments. We say what the extent of y is, put it in the integrand. If this is rotated about the x-axis, it's still 2 pi y. But now y here is just a variable. We don't put in the function of x. And here, the change is it's dx dy, not dy dx. So we'll see one of those problems there, but really the harder thing about the notes is connecting these formulas together and connecting these formulas together. If we can get over that bit, this part right here is just changing the role of x and y. It's not doing anything too different. Well, that's the initial discussion of what's going on. Now let's try to make some sense out of what we're looking at right here. Any questions or comments first so far? Okay, well, we start with C. It's a smooth curve defined by y equals f of x. Already there's a lot being said here. Recall when it says smooth curve, it's saying quite a lot right here. Smooth curve means f prime of x is continuous. That assumption is really important for us just so that we can guarantee this is an integrable function. Integrable function says that derivative there, whatever it is, even if it's not a derivative, it just has to be continuous as a function on the closed domain from A to B. So we start with something whose derivative is continuous. And let's plot this out. It could be described as y equals f of x, and the domain will be from A to B. So generic picture here, we're rotating about x-axis, so quadrants 1 and 4 are good ones to emphasize. We go from A up to B. Here's the curve. Y equals f of x. Notice it says we want a positive curve. That's because when we go to rotate this around the y-axis, we don't want things dipping below or above the x-axis. If it does, we can just break it up to where it intersects the x-axis, find the surface area on that part. On the negative end, reflect it above again, find the surface area of that next part. But this is more of a technicality, something to watch out for. I don't have any problems where we have to start breaking up integrals 3 different ways to try to get through it, but something to be aware of. We want positive functions, so there it are. There it is, and we rotate it about the x-axis. This is the hard part for me. I'm not an artist, so this is going to be a lot of us all using our imagination as we go to write this out. So if I really rotate this curve, first I want to just reflect it about the y-axis, the x-axis. One strategy here is to try to line up the points, relative heights. And then I'm just glad I'm using a digital pen. I'll give a couple tries here and we'll pick out the one that looks the best. Oh, geez. You know, it's not great. Let me try one more time. Kind of more like, maybe closer. Let's stick with this one. So that's the reflection of the curve, but remember the whole thing rotated. So that point rotates around, forming a circle. This is the part where it gets a little confusing. If this is a surface, you wouldn't be able to see that part as well, depending on how you're visualizing it, but you should be able to see that part. And this whole part, I'm not good at the shading, is the surface itself. The shading to me is the big struggle in making this work really well. But in fact, this is why Calculus 3 is hard to teach. You have to be really good at drawing 3-dimensional objects to illustrate what's going on. So we want the surface area here. The surface area is this lightly shaded portion right here that comes around like that. I think my dashed and undashed things look a little bit weird. It says integrate from A to B, and x ranges from A to B. Next thing we want to put on here is, here's a typical x between A and B. Now, as we think of that point, a radius emerges from here to here. That whole thing is going to rotate as well. And now we're looking at a kind of disk. It's right here where x was, and as x moves to the left, the disk gets smaller on that end. It grows until it gets to its largest out here on B. When it's at B, we're just looking at this whole thing. That's the front end of the surface. And if we take another look at this, the radius is exactly y equals f of x. So this is one way to kind of organize how this integral is derived. Our author puts in a pretty good amount of work showing step by step what the derivation is. But the main thing we're trying to do is show, if you have a random curve, how can you go from a diagram like this up here? Really, the surface area could be thought of as S equals integrate from A to B, a 2 pi times a radius times, you could say this whole thing, or just abbreviate it to ds if you like the differential. I'll just say the whole thing. Sometimes I think it's more clear just to write out exactly what you're working with. So you can rethink about your integral as really just being this. Then back over here, when we're looking at a disk or a circle altogether, it has radius y equals f of x, or just y. Then the rest gets put together in this kind of way. So that's all that's really going on in this kind of picture right here. Does that make sense to folks so far? Okay, there's a lot that goes on in this derivation. So if you're curious on how it goes, I would say take a look in the reading in section 8.2. Not a good one to bring to class. That one takes pages, it turns out, to get through. But this is just one way this problem can be worked. If the curve is described by x equals g of x, and let's say here, just to write in, just to be really specific about this, the curve is described by x equals g of y, where g is positive. Here's a part I would want to insert. And the curve is rotated about the x-axis then we get the same formula for the surface area, essentially. Notice it goes 2 pi y. Like we mentioned here, this time y is an independent variable. We don't substitute any function in there. But the structure is essentially the same. If we just swap x's and y's here, we swap it there, and put in the extent of the y-axis. So really, it's the same concept of this over here, just a different description of the curve. Now, the trickier one is this one. If you rotate about the y-axis, now you really have a big change in your formula. Our author starts to write out this way using the differential ds. I guess you're saving printing costs on ink by doing that. But if you want to express this out more completely, you would say S equals integrate from C to D 2 pi y, or excuse me, this would be A to B rather, 2 pi y square root, and let me try again on that, 2 pi x. Must have been a long holiday. We're going from A to B, 2 pi x. That was a struggle to get to that point. Appreciate your patience on that. Here we're rotating about the y-axis, and x emerges here. The ds in the formula is just square root 1 plus dy dx squared dx. So here's the new situation. To make sense of what's going on here, the big feature is we're rotating about the y-axis. So we still have y equals f of x. Extent of x is from a up to b inclusive. This time we'll emphasize quadrants 1 and 2 because of the rotation going this way. And let's just do a simple curve, easier to draw. I'll go from here A to here B. It's kind of a cop-out, but sometimes these are easier to plot than anything else. So here's my curve, y equals f of x. Rotate about the y-axis, and you'll have a point here that gets rotated out. Goes roughly to a point here, just trying to get the angle right. So rotation on this one, let's see, trying to visualize that rotation. We've got maybe circle going this way. A part you wouldn't see because this whole surface here is blocking it. Then I guess I'm kind of drawing it as if you're seeing it a little bit from an angle from above, which would mean you should be able to see that dashed line there. I should really practice this a little bit more often. Okay, so there's our surface. The front face of the surface is going this way. Over here is the back face of the surface, and we want this entire surface area. This is the integral, just like before. The extent of x, because it's an integral described with dx, is between a and b. So just drop a random x here. There it is, there's our x. The moment we drop that x in, it implies that there is a segment here, goes up to here. This whole segment also rotates, and when it does, we get a point here to here. We try to draw that in kind of roughly. And this gets emerged. So this whole thing sweeps out in that kind of way. Pertinent thing about this thing is, if we think in terms of what is the radius, that's the big question here. Over here, the radius was just the height of the curve, y equals f of x. That's because rotation about y-axis. But now if you rotate, sorry, I said that weird, rotation about the x-axis, if you do the opposite thing, rotate about the y-axis, the radius is just from here all the way to here. Radius equals x. So that's why x gets just dropped right into this location here, just to connect those two. Well, maybe let's leave that yellow. So again, if you can build a really simple diagram and you know the direction you're rotating, this one is just giving you x, and the one above is just giving you a y. Any questions about that so far on just seeing how these integrals get put together? That's too far. There we go. Okay, well, the first problem we'll do is kind of nice because I went to a textbook, almost plagiarized, but there is a citation here. It's not MLA or anything like that, but you can look this up. This is a pretty good textbook, I find, for nice graphics, which is something that is sometimes missing in calculus textbooks. So here's a problem where imagine you're building something. Let's say you have some just unrestricted access to a huge 3D printer and you're just printing things out. If you have to paint it, you need to know the surface area or those kinds of things. What we took is a curve y equals 2 root x. These are things you would program into your 3D printer. Gets rotated around in this way. So in blue, that's just a curve, y equals 2 root x. But as we rotate from 1 to 2, the actual bounds that we're concerned about, this little band right here rotates along with it and sweeps out to the surface. So we want to know what its surface area is, which means we're just going to plug everything into that formula. This is a rotation about the x-axis, so we can also say, pick any x between 1 and 2, and you have a height going up this way. This height is equal to, maybe a better way to write it, is this height from here to here is y equals 2 root x. So that's enough to inform us what should the integral look like when we go to put it together. Let's write it out here now. S is going to be a definite integral from a to b. The a's and b's are the extent of where x can be. You can either look down here, or usually this is a good spot. Go from 1 to 2. Now we want the circumference of this whole thing, if it's rotated out as a circle about the x-axis, there'll be 2 pi times the radius of that. That's the y going in. So this is the formula. On the next step, we drop in 2 root x. Last part is 1 plus dy dx squared dx. So that's the total formula. All we need to do is now break down each individual part so we can get the integrand nice and simplified, then integrate as normal. Any questions at all, folks, getting to this critical part here, just writing down the integral? Okay, well, in simplifying this integral, let's pause for a moment and just go to that spot right here. We have y equals 2 root x. We immediately want its derivative, dy dx. This is a shortcut for derivatives that involve a square root that I mentioned. Let me know if this looks a little bit weird. First, it's the constant multiple rule. And now every single time you differentiate a square root, good shorthand is it's just 1 over 2 root x. Does that make sense to folks on that shortcut for the square root? Awesome. That's, again, pretty common shortcut because these things come up a lot. We get a cancellation and we just have 1 over root x. So next thing we'll do is add 1 and square that quantity. 1 plus dy dx squared is 1 plus the square of this. That's just a 1 over x. And now that settles everything inside here. 1 plus dy dx squared is just a simple 1 plus 1 over x. At this point, we can return to solving the integral s. Let's do it down here. S is the integral where we take 2 pi. Those are constants, so you can chuck them outside if you prefer. Integrate from 1 to 2. Big step here is we have to take a substitution and actually put in right-hand side of this function here. So 2 root x goes in. Next, drop in what we just produced with that bit of algebra on the right. This becomes 1 plus 1 over x dx. Now, if we can solve this integral here, we're in good shape. And we're always a little concerned when we see a square root. You'll notice the algebra is kind of weird in section 8.1. But strangely, section 8.2, sometimes the integrals are a little bit easier. The fact that you put a y in front of your square root actually gives you a lot more to work with now. We can use a property that says root a times root b is the root of a times b. So that's what we have here. This x can distribute inside, and it's going to kill off that x in the denominator. So on the next step, there's an extra 2 in front. So collecting all the 2's, 4 pi, integral from 1 to 2, just 1 square root now. This x multiplies here for x plus, multiplies here for just a plus 1, and that's our problem to solve. That means this is a problem we could have done in a Calculus 1 setting. It's just there's not enough time to throw all these different problems in a Calculus 1 setting. But it's nice to know we don't have to do anything too fancy to this. For me personally, I would probably start off by saying it's 4 pi, integrate from 1 to 2, x plus 1 to power 1/2 dx. Now the antiderivative is just slightly easier to visualize. Copy in the constant 4 pi, multiply and add a lot of space, put in, well, not a lot of space, but a little bit. Put in x plus 1, its antiderivative is 1 power higher, so add 2/2 for 3/2. Once you have the power, multiply by its reciprocal, 2/3. And if you're a little concerned because this looks like it could have been a U substitution problem, also just mentally visualize doing this. D by dx of this part right here, starting where the red dot is where the antiderivative lives. 2/3, x plus 1, 3/2. If you differentiate that, the 2/3 and the 3/2 are just going to cancel each other out. We'll get x plus 1 to power 1 less, so subtract 2/2, it's 1/2. And then the chain rule says, multiply by the derivative of x plus 1. Done. So now we have exactly what we were doing with right here. For these kinds of functions, once again, even though you could do it as U substitution, if it's just an x plus 1, it's pretty much just integrating square root x itself. No extra adjustments have to be made here through the chain rule. If it was a 4x plus 1, we notice right away in our check things aren't right. But we just multiply by an extra 1/4, and that would satisfy it as well. Well, either way we look at it, here we have all this stuff has to be evaluated from 1 to 2. So those are going to be our next steps. The evaluation is going to take place right here. So I'm going to leave all the constants just factored off to the left so we don't have to duplicate them. So it's 8 pi thirds. Now we're doing the evaluation. This will be 3 to the power 3/2 minus, plug in a 1, it's 2 to the power 3/2. And that is the exact surface area of this object right here, whatever it happens to be. Maybe it's going to be something gigantic. It could be a new shroud to go over the damaged Chernobyl spot there to cover up the radiation leaking out. Something like that could have been what we're really trying to analyze. We don't have any units, but if you really want to think of this as a real physical object, you could say units squared. Really not necessary, but it's just a good emphasis. We found a surface area. Well, any last questions or comments with what we left with right here? Okay, maybe one last parting thought on this problem here is where the red dot is, in my view, that's a totally fine answer. We're going for an exact figure. So if you did want to throw this into a calculator, that's just to determine if the number makes sense based off what we expect. But sometimes our author likes to write out the solutions to these slightly differently. Very common way to rewrite these, it's just another optional way, this is full credit by the red dot, is you could say 3 to the power 3/2 is really just 3√3. 2 to the power 3/2 is just 2√2. And the way either one of those was determined is, if you look at 3 power 3/2, you could think of this as square root 3 cubed. So this time, this is square root 9, which factors in, or hang on, square root 9 times 3, because 3 cubed is 27. That's a quick fix right there. The root of 9 comes into as a 3. The irrational part just gets left behind. And that's all that's happening with the power 3/2. We just get the number times the root of the number. But we did it, folks. In either case, if this is something that you were interested in, maybe it's a weird wedding ring, looks painful, you'll know exactly the surface area on that thing. Well, all we're doing is practicing this in a couple more situations just to get a feel for all the different ways the formulas could go. So this is going to be our next version down below. Notice it looks weird because it's described as an x equals 1 plus 2y squared. We have an extent on the y-axis now, or the y variable rather, but we're still rotating about the x-axis. That part's pretty helpful in setting up the integral. It tells us fundamentally our problem, no different than the prior problem right over here. We're just changing the roles very literally for x's and y's. But another thing is, I would never throw an exam question at you like this. This is what the homework questions look like. But with a homework question, you can grab a graphing calculator, you could grab some technologies on the internet. You always want to get an extra view on these kind of problems. So if this was a real exam question, this graphic would be provided. Let's just do it ourselves. X equals 1 plus 2y squared. So we're looking at a parabola opening rightward as opposed to upwards. So nice little quadratic, but we have an extent on the y-axis. So throwing that in, 1 less equals y, lesser equals 2. That's what we're dealing with right here. So this curve, kind of innocuous looking thing, is just going to rotate about x-axis. So if you imagine that this isn't a real exam question, this is similar to how they could go. This is provided, and it's just meant to help us set up the integral. So the way we do that is, you might want to write in that this is x equals, let me just write in as 1 plus 2y squared. Then we go from 1 to 2. That's an extent on the y-axis. On the real exam, I would probably want to write that in. Go from 1 to 2. Now the next thing is, if the extent on y is from 1 to 2, you want to put y somewhere, say, over here. So y goes into this location. We go to some spot here, and then this whole thing is rotated about the x-axis in that way. That means this point is rotated, and the radius, once it becomes an actual circle, the radius of this would be equal to just y. Well, that's the height going this way. It came from over here, and that's all you produce. This time y is a variable. It's the independent variable, so we don't actually substitute anything back into it. We just use y as if it was x. So this is the stuff I would probably draw in if I was wanting to be really sure we build the integral correctly. Now let's build the integral. S for surface area, or you could say, if you want to be specific, because that looks like an integral sign on its own, you could say SA, just to be hyper-specific. This is an area. We'll integrate from extent on the y-axis, go from 1 to 2. It'll be 2 pi y, then square root 1 plus, here's the next change. If x is specified this way, inside here you'll go dx dy. So we flip that around, square it. Second thing that happens is if we have y as the independent variable is always indicated this way in the integrand. So dy goes here. Now everything is in line. All we need to do is integrate, and we'll be on our way with this one. Oftentimes, this is the hard part of the problem. And because these can be long problems on their own, in exam situations, sometimes they'll be asked, find the exact surface area. Other times you might be asked, just set up the integral and then stop. The concept would be, do you know how to set up the integral in that case? That just makes the exam doable in a 75-minute timed exam setting. But now we're doing this one top to bottom. So next thing we want to do is compute dx dy. We can do it over here on the margin. Dx dy just means you're differentiating this with respect to y. That's a nice derivative. This is just 4y. So that's all said and done. Next portion, add 1 and square. So 1 plus the last line squared. Let me try again. Just so common to want to write dy dx, but everything's backwards now. It's dx dy. So 1 plus dx dy squared is 1 plus 4y squared. So we're dealing with a 1 plus 16y squared altogether. So that goes into this spot. And now we're about ready to go. This is equal to, let's maybe keep it on the left here. 2 pi, I usually just kick outside so it's less of a distraction. We usually want to focus just on the integrand primarily. So we have a y here, and then a root of 1 plus 16y squared dy. Now, we just went through an exam where one of the most powerful integral tools we found when a square root comes up is trigonometric substitution. And it works here, but you never want to work too hard if you don't have to. Anyone see another approach? On the prior problem, we were able to just distribute square root x inside and it cleaned things up for us. Here, you don't necessarily want to do that with a y. Sure, you could say y is equal to root y squared, since y is only positive. That would really work out, but less helpful here. But we've got a chat. In the chat, the question is, isn't it a 2 pi x? Let me see here. For a rotation about the x-axis, it would imply that this curve here is rotating about the x-axis, and we would have to use a y in place of this location here. Is that what you're referring to, Brian? Yep, you betcha. And honestly, to me, this is one of the things that's really confusing about all of our integrals. Even if it's specified as an x equals, it's the way you rotate, either about x-axis or y-axis, that determines what goes in this location right here. Again, really kind of tricky. Looking again, just as a refresher on these notes, it's either going to be this deal if we rotate about the x-axis, we throw a y in, or it's going to be this deal if we rotate about the y-axis, we throw an x in, and we still haven't actually gotten to that particular problem. So even if it's described in this really weird way, a y still goes in there. And I included this extra emphasis. I think I typed this verbatim for the author's notes, so this would be an edit right after the fact. Even if it's described as x equals g of y, this knowledge that's rotated about x-axis drops in a y in that location. So back to our problem. We're dealing with a y right here. We could redo that last trick where we distribute in a square root through that formula. But that's working way harder, and I don't think it would really actually help us too much, in all honesty. There's still one last trick. Anyone happen to know what could still allow us to integrate this reasonably? Absolutely, good call. Just because a trigonometric substitution could work doesn't mean you want to use it. Always reserve trigonometric substitution for when you have to use it. If it's an ordinary u substitution, that's the best technique to use. So let's do the u substitution. It's a good call on this one because if there's a y here, that's in some sense a constant multiple of the derivative of this entire inner function. That ought to be our u then. Set u equals 1 plus 16 y squared. Differential would give us 32 y dy. So that's going to help us get rid of this portion right here. The y dy is, well, not quite what I want. Let's do a division of the 32 constant. 1 over 32 du is y dy. So where we see y dy right here, we're just dropping in a 32 of du, which means this is a good opportunity to swap the limits of integration as well. We're going to say the limits are from extent y equals 1 to y equals 2. Drop that into our u, and we get u is 1 plus 16 by 2 squared. That's 16 times 4, which is 64, plus 1 will give us a 65. And last one, drop a 1 inside here. That's just a 1 plus 16. So now we're integrating from 17 to 65. Large numbers, but that's just because of our u in the substitution. But I'd say at this point, everything is kind of falling in place. Copy in the 2 pi. Substitution already from y dy produces 1 over 32 outside the integral, or inside if you prefer to leave it there. Next change are these values. Go from now 17 to 65. And where it was this, we just have root u, which means we can express it as u power 1/2 if you prefer, du. So that's all the substitutions at once. And now it was something awful to start, and we have a very friendly integral to conclude. Again, section 8.1 is strange. It's harder to integrate in section 8.1, but 8.2 is harder to set up. So that's the kind of dual challenges with these two sections. But we're just about done. All we have to do is finalize this. First division 2 into 32 gives us pi 16ths. Multiply and give it some space. Now antiderivative here, in a very real sense, we did the exact same antiderivative in the last problem. U goes up by 1 power, it's 3/2. Multiply by the reciprocal 2/3. And evaluate the part that varies, just U, from 17 to 65. Once we do all that, we'll have the exact surface area. So first two divides gives us pi over 8 times 1/3. So pi 24ths. And I mentioned before, you can express these in different ways, but just to signify this is a valid answer as well, I want to leave this answer in the form 16 power 3/2. There's a lot of simplifications you can do right here, but if you're moving on to the next question just to focus on the calculus, I would understand. You're not getting bogged down in the arithmetic. Yeah, go ahead. Oh yeah, that's a weird copy error. Thanks for spotting that one. It was 65 here, should have been a 65 there as well, which then bounces down to here as another 65. Again, thanks for spotting that one. Okay, this one doesn't simplify as much. 16 power 3/2 is a lot of work. But this one, if you want to rewrite it, you probably would just say 65 root 65. We'll leave it in this format just because we want to say it's a valid way to express it as well. Lower limit is just minus 17 power 3/2. And that's our exact surface area. We can end the problem right there if we prefer and move on to the next. We're going for the exact numerical result in these kind of problems. So this is the answer I'm looking for, but there's no harm in approximating these if you wanted to. Let's do that on this one, just for the sake of, sometimes that is a great problem solving technique. Seeing the evaluation of this can tell us if we're even on the right track. For example, if I get a negative number, all bets are off. There's a mistake somewhere, right? So it's pi 24ths multiplying 65 power 3/2 minus 17 power 3/2. And that tells us it's about 59.4 units squared. Okay, so again, this is just a form of a check. This is the answer that we need for full credit. And this one is, I guess like we said in the other application, this is the sanity check. By actually evaluating the number and see what we get. So that's the whole process. And both of these problems are really basically the same. This curve was just weird because it was specified as an x equals. That was the only weirdness about it. For the next one, this one is a lot different out of nowhere. And what makes this one very, very different is that right there. We're rotating about the y-axis this time, which means we do need to change things around a little bit when we go to write out this integral. So let's give this next one a try then. First thing we would do is, in a real exam setting, let's take a look at the graphics that would be provided. So we've got a function, y is a fourth, x squared minus a half, natural log x. If you use Desmos, always put in the domain if you're using this to help with homework. 1 less equals x, less equals 2. And that's it. We're rotating that about the y-axis. Not a whole lot to see here, but that's our curve finally. We just get a good window here for a screenshot. So we go way out from -2 all the way up to +2. There's our surface. This is a y equals, I'll just abbreviate this one to f of x, this being the f of x right over here. And now if we want to visualize what's going on with this one, grab an x between 1 and 2. So I just draw it in this way. It means we have a portion that goes up like this, and this part of the curve rotates about the y-axis. We now have a line segment going from here to here. See if I can get that just right. So according to this rotation, notice I haven't attempted to even plot the surface, but if we tried, it would probably look about like, oh geez, something like this. So that's the other end. So we have a surface that goes about like that. This is a really shoddy graphic, but you get the idea. Let me take off some of this so it's not too much of a distraction. The major thing we wanted though is this portion right here. This is the radius of the circle that would be generated when this whole point rotates all the way around. And the radius this time is, well, we're looking at it. The distance here to here is just x. So that helps us set up the integral because now we can say the surface area, S or SA, or just A for area would be totally fine, is integral as we integrate from 1 to 2. We need to put in 2 pi times a radius, but when we rotate about the y-axis, it's just x. And that's nice. It's kind of similar to the last problem. This is a variable. We don't have to throw in a function like we did on the very first problem. The rest of it is just the 1 plus dy dx squared dx. So like we mentioned with a lot of these problems, the challenge is more on setting up the integral, determining if it's going to be x or a y here and that kind of stuff. The rest of the work that we're going to do on this, pretty similar to what we did in the last section. But we ought to finish this one off now that we put it down on paper. Any questions at all, folks, on the setup? Okay, as we go to solve this one, it might feel like deja vu on the problems you were solving in section 8.1. This is one of those problems where the algebra is rigged just right, and we have to factor very, very carefully as the only option of eliminating the root, or we could be stuck on this question. So if that happens to you in your homework, don't hesitate to take a picture of it, send it to my email, or show up in office hours. I'll be very happy to see and help out with the algebra. Let's start way up here, dy dx. And just to emphasize, you don't have to love Leibniz notation. You could just write out y prime. Sorry, I'm having trouble with the red dot. There we go. It's not going to, I think it's just tired. We'll go y prime equals, differentiate this, and we get a half x minus 1 over 2x, the x dropping into the denominator coming from the natural logarithm. And now we're at that part there. Next thing we'll do is just square it. So y prime squared is a half x minus 1 over 2x squared. So expand all this out. We would have to square the first term, which is now 4th x squared. When you multiply here to here in the FOIL method, you just get minus a fourth. And then you multiply here to here again, you get minus a fourth twice. They sum to minus 1/2. This is the deja vu part. That minus 1/2 is highly specific, going to help us factor. Next, square that part, so you get plus 1 divided by 4x squared. And that's just the dy dx part. Now let's include the 1 plus on this. So 1 plus y prime squared is just adding 1 to this whole thing. And when you do that, it's 1 minus a half. That part converts to positive 1/2. Let's actually write this in just for clarity. 1 plus 4th x squared minus a half plus 1 over 4x squared becomes, combine the like terms, keeping them in the middle, 1 over 4x squared plus a half plus 1 over 4x squared. Finally, this does in fact factor as power 2. We take the square root of the first term, 1/2 x. With these signs, it determines the sign in the middle has to be positive. Square root of this term is 1 over 2x. And ordinarily, you'd want to verify that just by literally FOILing it out to make really sure that we've got the right thing. I'll leave that up to the class. Does it look okay to folks, or should we FOIL it out just to be sure? Okay, some thumbs up so far. How about for folks in Zoom? Does that look all right so far? Okay, looks like we're in agreement. This is the algebraic form for 1 plus dy dx squared. And the most critical thing about it is we have to square root that quantity. And we're in business because power 2 is going to cause a cancellation. So this is the hard part of this integral this time, just strange algebra to get to the integrand in a simplified form. But from here on out, we can now kick out 2 pi, pretty much copying our last methods. Integrate from 1 to 2 of x times. I want to show this little substitution here just to connect the dots, but if you just put in a half x plus a half plus 1 over 2x, that'd be fine. So here it is with the power 2. On next step, we'll do a cancellation. So this is 2 pi. Integrate from 1 to 2, x times 1 half x plus, and let me fix my penmanship on that. It looked right when I was writing it in, but you have to be sometimes really careful with penmanship. I wouldn't be hyper specific about marking off points if I saw something not just right. But if you write something not just right once, you have a habit of copying it down incorrectly a bunch of times. That's my habit, at least. So let me fix this right here. Should have been plus 1 over 2x. That makes a world of difference now. So 1 over 2x here as well. Dx. Now, this is a very friendly integral. We can say that this equals 2 pi. Integrate from 1 to 2, distribute x inside, and we have a half x squared plus 1 half dx. At this point, we're just running through the ordinary methods. Go 2 pi. Antiderivative goes here. New power is going to be a 3, so this will turn into 1/6 x cubed. You know what? That's a good idea. That would simplify quite a bit when we do the evaluations over here. And those kind of simplifications do matter. If you're writing down constants a whole bunch of times, it's easy to just kind of lose your way with that. So I like that approach. Let's take out that 1 half. 2 pi times 1 half factored out leaves an integral from 1 to 2 of just x squared plus 1 dx. It's a simple change, but it's profound in the actual work you write out. This is going to make this a lot more streamlined. So good call on that one. It also causes an immediate cancellation here that we don't have to do down the line. We just do it at its easiest step right here. And next step would be pi times. Use your expression now. Now this is a third. X cubed plus x integrated from 1 to 2. So if we can get the exact value here, we're all set. This becomes pi times the result of throw in a 2 first. It's a third. 2 power 3 is 8 plus 2. Now throw 1 in, the lower limit of integration. We'll get a third plus 1. And that's a whole bunch of constants. I want to reiterate a comment we did make on exam 1. On exam 1, if you got to this spot, all the calculus is done here. You do have to do this evaluation, but this would always be full credit on exams. On homework, we do have to simplify that, so you could lose a half a point if you just left it in that form. But this allows us on an exam setting to just focus on the calculus purely. And if you stop at the arithmetic, I'm not as worried about that. But we're doing this as if it was a homework problem, so let's keep on going. We have pi times. This is 8/3 here. Plus, in terms of thirds, this is 6/3. Minus, this is a third plus 3/3, which is 4/3, so we're taking away 4/3 altogether. Fractions always make me a little uncomfortable, but we have thirds everywhere down the line, so this is really just a 8/3 up to 14/3. Oh, sorry, question first. Gotcha. Thanks for looking though. This is stuff I mess up quite easily, especially at the late hour. So it looks like altogether 10/3. So pi times 10/3. If I did that last step right, or pi 10/3 if you prefer in that format. Hang on. I think it looks a little bit better this way. 10 pi thirds. For some reason or another, this is just a more visually pleasing way to look at it. You don't have to be that specific with how you write your results. That would have been perfectly fine right there by the red dot. But we've got a value, folks. This weird looking surface, it would be like a bowl with, well, maybe not a bowl, there's a huge hole in the middle. But whatever this is, it has exactly that as its surface area. Any last questions at all, folks, to this step? Okay, so this pretty much covers the different situations that you're going to see come up on the homework assignment. I have one more question here. The trouble with all of these problems in section 8.1 and section 8.2 is that they are massively, massively rigged problems. They're rigged to work out just right so that when you get to this step, we don't have to do any kind of approximation. It's integrable by finding an ordinary antiderivative. That's not always the case. You can take something that looks like it should have been a simple curve, but the integral on this one is fantastically complicated out of nowhere. This is a good use of Simpson's rule. I didn't ask one in the homework assignment, which means I'm probably not going to re-ask this whole question on an exam setting. But think of this as just practice doing the Simpson's rule again, essentially an exam 2 review question. It is a little bit tricky, so we're going to take our time with this one. We don't have a lot of time with it. So what I propose is let's set up the integral here. Then on Thursday, we'll come back and hit it with Simpson's rule so that we're not breaking the problem too badly in the middle. Does that sound all right to folks? Okay, let's hit this with the setup then. It's an ordinary curve. We're rotating about the x-axis. That's the ordinary direction. The oddball one is when we rotate about the y-axis. But first, to get some intuition on what it all looks like, let's still go y equals natural log x. 1 less than or equal to x less than or equals to 3. So this right here is going to rotate about x-axis. Okay, we've got it. So let me just shrink this down just a touch. Next thing we can say here is if x goes from 1 to 3, here's a particular x. And if we rotate this about the y-axis, this line segment here would also rotate along with it. What that produces for us is a radius of what would become essentially one big disk once this rotates. And what we want is radius, which is equal to the height of this curve. But we know the height of the curve is just describing the function, natural log x. So now this tells us if we're going to integrate this thing, well, if we're going to approximate the integral itself is going to look like this. S equals integral from 1 to 3, 2 pi, y goes inside right here, but y is also natural log x. Let's drop that in. It multiplies the square root of 1 plus dy dx squared dx. And when we go to hit this with Simpson's rule, we're not going to say exactly what it is just yet, but when we go to use Simpson's rule, we'd be taking equals 2 pi times S6. So what I mean by that is we're kicking this part out of the integrand, much like how we factor out that 1/2 and did a cancellation like you suggested. No reason to do Simpson's rule with a constant inside. Just kick it out. Now Simpson's rule is going to be relative to this as the integrand then. So we want to say what that integrand is exactly, and then run through the whole process. Turns out with n equals 6, our answer is going to be accurate to, I think, the nearest 1,000. It's pretty impressive. But this is a good one to come back to when we're in the next class, Thursday. Oh, because if it's about y-axis, you would put in a y right, or excuse me, an x right here. Yeah, I agree. Then everything just kind of goes nicely. Turns out, yeah, this is the weird rotation on this one. The integral is just outrageously hard out of nowhere. Yeah, good observation on that one. Other questions or comments so far? Okay, we'll come back to this. Think of this as just another review of Simpson's rule and surface areas all at the same time. And then our major thing we'll take a look into is applications to physics and engineering. This is a big section. We're going to look at hydrostatic pressure and centroids, and there's some pretty interesting applications. One of them at the very end is not an application we can really do in class, but it's kind of like this application over, oh geez, I'm losing my spot. It's kind of like this application. It's sometimes neat to just see how this stuff can be applied, even if it kind of leaves the scope of our class entirely. So we'll take a look into all those next time. Have a great night, folks. And if I didn't return your exam, don't hesitate to email. I'll be happy to scan them on Friday. But take care. I'll see you all in Thursday's class.
I had a question on example 3.
Yeah, let me take a look at that with you. Okay.
Yes. So the 1/2 x plus 1 over 2x squared on the right there.
Over here. Gotcha.
Yes, that is 1 plus uh, the derivative of y squared on the left
Yeah.
of it, right?
Yeah, this should be, to be more specific, carried all the way down like you're mentioning. And yeah, that's what
Okay.
this side is referring to, which is
And
just
then how
really
do we,
great. Sorry, go ahead.
uh, what were you saying about the on the left there?
Oh, the dy dx is just being shorthanded as a y prime, just as a shorter way of writing it this time.
Oh, okay. That was where I was lost. Okay. Thank you.
Gotcha. I just said right away that y prime, if you prefer, is just the Newton's prime notation as opposed to the Leibniz derivative notation.
Okay. Thank you.
Yep, absolutely. Have a great night.
You too. Bye-bye.